in the interest of time, I'm going to go through what I want to try to get to here. I'm going to skip. Okay, I want to get to this point right here. So for the moment, I haven't given you an equivalent circuit, but you know what it's going to look like, right? What we're going to do is we're going to end up with, I got to put a little equivalent voltage right there. We're going to end up with a per phase equivalent that looks a lot, what do you think it's going to look a lot like? Any takers? What do you think our equivalent circuit's going to look like?
A lot like a transformer, beams for a transformer.
Absolutely, it's going to look like a three-phase transformer, isn't it? That's exactly right. It's going to look identical to it, actually. We just are going to identify. So what do we have? We have a winding right on the rotor, on the stator. Typically, they call this R1. There's a leakage, JX1. So we're back to this transformer. We have to do the full circuit. There's a magnetization. So there's going to be a magnetizing branch, JXM. So I just drew the stator, and it's like a transformer. There's going to be a transformation. It's kind of complicated. Unfortunately, I'm going to have to wave my hands a little bit on this one and not go through it in rigorous detail as to what this turns ratio is, because that's where the magic is. But essentially, you can transfer energy across to the rotor. The rotor has a leakage. We could call this the JX rotor. It has a resistance, right? Now what happens is, quite simplistically, we just shorted it, didn't we? So there's a resistance here. And what happens is this resistance changes with slip. So this would be the rotor resistance divided by the slip. So if the slip goes down, this goes up. If the slip goes up, it goes down. The resistance changes on the rotor side with slip. And this includes the losses, everything. This is typically what we call the power that gets applied to this side of it, would be the gap power that gets applied. And then the power, if you split this circuit up, well, first of all, let's just get everything, let's move everything over and refer it to the stator side. So we'll end up with our per phase equivalent circuit that looks like this. This is the voltage that's applied to the stator. I'm just going to call it V1. There's a current, I1. It's the same as, you could call this V line to neutral A stator if you wanted. It's a line to neutral voltage of one of the windings. We picked the A winding, ABC windings. We aren't going to ignore the resistances anymore. So we've got, remember with the synchronous machine, we ignored the resistance. We don't anymore. R1. We can't ignore anything, actually. Maybe we could ignore the core loss. So one of the problems has core loss in it. This is x1 here. This is the magnetizing reactance. There's a core loss. Looks just like the single phase equivalent circuit of the transformer. I'm going to call this JX2. This is actually equal to JXR prime. So we don't worry about the turns ratios or anything on this because they all kind of fold into each other, and unless you're a machine designer, you really don't care. And then I have another resistance here, which I'm going to call R2, and it gets divided by S. And there's a current here, which is the rotor current referred to the primary side, which I'm going to call RI2. And we're going to be, next time we're going to use this circuit. We're going to solve problems with this circuit. This is what you need to know. Now there are different ways. The last point I want to make is we're ending up here is that I want to make two final points. This is there's a power associated with the current through that, right? So if you said that you could just take the magnitude of the current, phasor current, whatever that is, times R2 over S times 3. That's a power. You got to put the 3 in because we have 3 phases. Otherwise, you ignore the other 2 phases. That is equal to two things. It's equal to the P loss of the rotor plus what we're going to call P mechanical, which is what you're applying to the shaft. And you could actually rearrange this thing then, because we know that the P loss of the rotor, we have 3 windings. They've got 3 resistances effectively. So we have I squared loss in all 3. That's going to be equal to 3 times I2 squared times R2, which is the physical resistance of the rotor winding. We do everything referred to the stator. We don't worry about the turns ratio as far as between the induction motors, stator and rotor. We're going to kind of ignore that. So we basically could rewrite this equation and say that we have 3 times the magnitude of I2 squared times R2, that's the losses, plus 3 times I2 squared R2, 1 minus S over S. And so we have broken it up. This is the P loss, and this is the P mechanical. So we know the P mechanical, from which we can find the torque, is 3 times the current in the rotor squared times R2, 1 minus the slip over the slip. That's your mechanical power applied to the shaft of the rotor. We can also revise our equivalent circuit if we want to show how we're breaking this out. So we could write it like there's going to actually be three possible forms. We may not have time to go into much detail on the third one, but this is the second form of the equivalent circuit. R1 JX1. Got your core loss here. JX2. Now I can put my resistance of the losses broken out. Now this is a variable resistor with load. This is R2 1 minus S over S. And we can also say this voltage here, I'm going to call this E2. That's essentially your back EMF voltage. Now if we go back up here, this is variable. So the resistance varies with load. We did kind of laid the foundation, and you could start doing homework problems with a little bit of study in the textbook and the notes. Any questions? I want to show you something from, let's go to the animations that we have here. Crap. What is this thing doing? I hit a button that it doesn't like. That's a stupid cursor.
Did you hit the center, the scroll on the
yeah,
mouse?
I don't know. Yeah, I don't know. Yeah, I wish you wouldn't have so many stupid buttons on these mouses. It just drives me nuts. Okay, yeah, thank you. That was it. Okay, animations. And I want you to get a little bit of insight onto the induction motor here from these animations. And I'm going to show you again to review. We've got, this is your equivalent circuit for an induction motor. So it's three-phase windings. They could be delta windings or Y, and I make a little correction to this drawing that in reality you do have a little voltage here to effective. It's an effective E voltage, and you'll see in the circuit what that really means when we go look at that again. So you have a three-phase winding, and then you have on the rotor another three-phase winding, and then you short circuit the outputs of the winding. And what happens is if you apply a voltage, three-phase voltage, to the armature winding, it creates a rotating MMF that induces voltages, the EA2, EB2, EC2, into the rotor and causes currents to flow. Then it, in opposition to kind of the interaction between the torque produced by the current in the rotor, or the MMF and the flux, it's basically very similar to the idea of, you have a magnetic field, and then you've got kind of that armature effect of things working against each other, working with each other, however you would say it, and the rotor starts to move. It'll move. And it's because you've got the current flowing in the three-phase winding, it's like you have an electromagnet on the field. Just like, you had an electromagnet on the field of the synchronous machine that was applied from a separate source, and it was a DC. Now this is an AC electromagnet at a different, it ends up being a different frequency. I'll show you that in a moment. But this is really a fantastic machine. Very interesting how it works. And this is, I think, well, as I've said, the greatest invention ever was this machine by Tesla. He figured this idea out, and essentially, remember, we talked about three-phase windings that have alternating currents in them, and the alternating currents are 120 degrees phase shifted from each other, which could be produced by, upstream three-phase generator. So you can see, remember this curve, you've got the A windings red, see the amplitudes going positive and negative. The B is green, doing the same thing, and then the C is blue. But if you instantaneously add up all of those currents, you can see this black line is this like a sine wave that's moving from left to right. So you have it's a motion. So the MMF, this was on the synchronous machines. So the stator winding is the same for the induction motor, produces this MMF that's moving in a direction. Now what, for those of you who may have seen this or had some experience with induction motors, what do you do if you want to change the direction of the rotor? Does anybody know?
You flip the phases.
That's right. All you have to do is flip two of the phases. So you could flip A for B, B for C, or C to A. It doesn't really matter. And then it goes in the other direction. And that's a lot of times people think of talk about positive sequence, negative sequence. For those of you who've had power classes, you can break things up into positive, negative. There's some loose relationship here in that, it's in that the positive sequence relates to the movement of the field in the polar domain. So it's kind of like we've been talking about this all along, and you've got this vector, and if you're moving in this direction, that's the speed of it, and your angle, theta E, it's going in this counterclockwise direction. You would call that a positive sequence. And it's typically the way I have defined the phase relationship of A, B, and C, where the B is negative 120 degrees and the C is positive 120 degrees out of phase with the A. That is called positive sequence. It would be moving in this direction. If you went to B plus 120 and C minus 120, that would be negative sequence. Or negative, it'd be going in the other direction. So it moves it this way. And in the power classes, when you study positive and negative sequence, what that means is that you actually have both of them at the same time. And that's what happens when you unbalance any one of the windings. That could happen in a motor, or it could happen in a power system where you create a unbalance or a short circuit across one of the windings. That would give you a negative sequence component that adds up at the same frequency. So everything here is happening at the same fundamental frequency of omega E. So anyway, a little aside there, but because you've got this is what Tesla figured out, this whole idea. And he demonstrated that you could create a much better rotating machine, which you could then use to do work like run mills or do factory work. I mean, the whole Industrial Revolution was based around being able to turn things, to move things because that's really how most work gets done. Whether you're pumping something or rolling something or moving something, it's with a rotation. And he demonstrated that you could, what he did, I don't have a I actually finally found it online, and I got to dig for where I put it, but he took a egg-shaped, like it'd be like an aluminum sphere, but then he made it kind of egg-shaped. So it's aluminum conducts current, and then he put it in, set it up on a table with the windings set up this way. Like you have the A minus, and the B minus, C minus. He energized these windings and it showed this thing moved. He spun the egg, and it's like, wow, this was at this World's Fair demonstration that he did, and he proved that you could quite simply create a motor without all of the commutators and brushes and all the garbage that was in the DC machine that was really Edison's big thing. And what this meant was it really dictated three-phase distribution, because three-phase power plants, if you could create this three-phase source all over everywhere and distribute it, and you could figure out how to build these motors efficiently and effectively, you could just plug them into this and you've got a motor. You don't have to do anything else. And it really literally did cause the Industrial Revolution. And it really dictated why our power is distributed in three-phase AC, because of this motor. Now the induction motor, the windings on the rotor are something to think about, because you could wind those windings on the rotor, but from a manufacturing standpoint, that's still a pretty complicated thing to do. So the egg isn't a really efficient way to produce torque, definitely, but kind of coming off of that idea, the squirrel cage induction motor was developed. And what the squirrel cage induction motor is it's simply, you can see it really well right here. You have aluminum bars instead of windings. So you know how we distribute the windings in slots. You just take these bars around this thing, and then you put a conductive aluminum ring on both ends. You cap it and weld it together, and you've got this, it's like a squirrel cage, that squirrels run around in. And essentially what they do is they make the core material, and they treat it kind of like a casting, and then they pour the molten aluminum into it, and it fills it up, and now you've got a rotor. It's quite easy to do. I mean, very effective. They have these little, these aren't straight bars, because the little skewing reduces the ripple makes the motor turn in a smoother way. So anyway, that's the squirrel cage, and that's really the main thing that's used for induction motors. And there's an animation of that here, which I had, and let me see, every time I do it, it's like, where is that stupid thing? I don't know. I was going to show you this, and I've got some pictures, but essentially what's happening is you're running the MMF through the field, and you just got these conductors. You don't care whether they're A, B, C, or D, but it effectively impresses another rotating MMF, which mimics three-phase, onto these rotors. So that's the magenta here, caused by the flux. So it's kind of like the magenta is your armature, and the green is your field winding, really. It's there isn't. I'm going to talk to you a little bit about that, but there isn't exactly a armature or a field winding that could be identified here, but that effective action is happening. And all right, where is it? Squirrel cage. It's not, there it is. So this shows you what the squirrel cage is. It's just moving around like that. It's got the two end rings, and it rotates inside of the stator. And you can just imagine that there's core material around all of this. Okay, straightforward. Okay, so these are some pictures from the textbook that show this as well. So what we have here, first of all, is we've got a flux. You can think of that, this thing right here is the flux that's moving because of the excitation of the three-phase stator windings, and it moves at this synchronous frequency, right? Now the synchronous frequency is the speed of the flux. It relates to the electrical applied frequency in this way. 2 over poles times the electrical frequency, where omega E is 2 pi times Fe. So 60 hertz, say you would put that in there. And remember, in the synchronous machine, the rotor frequency or the rotor speed is equal to the synchronous speed or frequency. So then you've got these induced MMF into the rotor, and you end up with another, this is an MMF. We can kind of think of it like we're thinking of the armature before, that's moving with it. There's a difference of an angle here, and this is a very, very interesting thing here. So you remember that in the DC machine, we wanted to have, this is the field MMF here, and we could get maximum torque per ampere if we maintained a 90-degree relationship between these two, and this would be like a torque angle here, okay? And so the blue is the MMF of the rotor. It's going at a different speed. The speed of that is the rotor speed, or that's the same as the mechanical speed that we talked about with DC machine. So rotor speed, mechanical speed, they're the same thing. It's the rotor flux speed or mechanical shaft speed. Now this shows the relationship between that rotor MMF and the field created by the stator. So this again is kind of like the green that we've been using for field, and blue. And notice the displacement between these peaks. Let's see, displacement between 0 points, easier to look at, okay, because they're not at the same frequency. You also see, notice it's quite clear what's the period of these guys. You can think of this as the 1 over the, 2 pi over the synchronous frequency. That would be like that period between zero crossings of the field applied stator MMF. And it's really not, you can't really always say it's a field, it's a armature. But there is, it's close to a field. The stator's close to a field, and the rotor is close to an armature in the way they behave. But what happens if you look at the zero crossing point differences, there is a 90-degree difference, which is most of that difference of angle difference, plus this little phi here. So we remember that we had this relationship of, let's see, I thought I wrote it down up here somewhere. Now I'm going to rewrite it here. So we had this relationship of torque that's proportional to negative of a sine of del. And so this angle is del. That's the torque angle. Well, with the induction machine, you just have this, I'm going to put a little k here that represents kind of the mixture of the field, equivalent field, and equivalent armature, MMF, and a negative here. And so being a motor, it's like if you could have del equals negative 90, you'd have max torque per ampere. But you can't get there because of this little angle. Now this angle, phi 2, is relates to the rotor leakage inductance. So if we go down and look at our equivalent, oh, here it is right here. So if you look at your equivalent circuit for the rotor, I mean for the whole motor, for this is a per phase equivalent circuit that we derived last time, you actually have a voltage E2. It's like a back EMF. Remember that this is kind of equivalent to, it's really equivalent to the d lambda dt from Faraday's law, and that voltage gets applied to the rotor. So this is the rotor circuit right here. And it's applied across the air gap. So you have your air gap here, and it looks purely resistive. So if you're looking, except for this. So if you ignored this guy right here, it looks like a resistor. And if you kind of look at, okay, so I've got a unity power factor looking this way. If I look this way, it looks, you know, it's just like E is J XM times whatever your current is going down that branch there. You could say divide by square root of 2, assuming, you know, so kind of it's very similar to, we had the E for the synchronous machine where we had JXAXAF times the field current divided by square root of 2. We had E for the synchronous machine. So there's really a 90-degree, because this J is 90 degrees. There's a 90-degree shift between these two, except for that. And so the leakage inductance keeps you from getting max torque per ampere, but if it wasn't there, you would actually have an ideal machine that could get the best torque per ampere. Just build it and it would work. But now since physically you can't do that, that's where drive controls come into play. And if you've ever heard of vector field-oriented control machines, all they really do is they work to orient the phases between the currents to cancel out the effect of the leakage inductance. It's very complicated, and it's dependent on estimating what that value really is. And the whole science of induction motor, high performance induction motor drives, is all about estimating parameters, estimating fluxes, and operating without a speed sensor or position sensor. That's really the entire science behind motor drives and induction motor drives. So any questions about that?
No.
It gives you, okay, everyone else, at least one person gets it, I think. Everybody else is like, what the heck is he talking about, right? But hopefully this is becoming clear, because I want to now just jump into the real mechanics of solving problems with induction motors. The last time someone in class very astutely pointed out that the equivalent circuit of an induction motor should look like a three-phase transformer. And it does. So this is the per phase equivalent circuit. And in this per phase equivalent circuit, we've got pretty easily identifiable things here. We've got the stator winding resistance. We've got the stator winding leakage, the rotor winding leakage referred to the stator side. We've got the rotor winding resistance, we've got the core loss resistance, and we have the magnetizing branch. Now in the induction motor, you cannot ignore these. You at least have to have one or the other in there. They both affect the operation. Like in an exam, I would probably give you one or the other. I'd say the RC is nearly infinite, or the XM is nearly infinite, and the other one I'd give you a value, but if you don't get a value, assume it's infinite. Normally it would be XM. I would, because there's always magnetization, so I'd probably, if we were going to ignore anything, it would be this guy right here, which means RC is approximately infinite. So it'll change the answer a little bit. You'll get the chance, if you want to look at that on the last homework problem. It has an RC, but you could look at it with that infinite and see how much it changes your result. If you ignore this branch, you will get a significant difference in your result, and it won't be the right answer. Now, the one thing that we talked about last time, you say, well, what's this little s here? That s varies. It's called, we talked about it last time, it's called slip. And slip represents the difference between the speeds of the synchronous flux and the rotor flux. And so let's go up to and talk about that a little bit here. So what we have is we have two speeds. The speed associated with the synchronous flux, or you could say stator even, you know, the little s could mean stator or synchronous, and a little r, rotor. That's the rotor MMF speed. So that's, you know, this is associated with this guy, and this is associated with that guy. And the difference between them is what is called the slip speed. So I'm introducing this a little bit differently than we did last time. And we're going to, the slip speed is a percentage of the synchronous speed. There's a small difference. You could say, well, let's just say that that difference is a fraction of the synchronous speed, because I can always get the synchronous speed. I know, if I know the frequency that I'm applying to this, to the windings of the stator windings, that's this value, you know, right here, that's 2 pi times whatever the electrical frequency is. I've got that frequency, I've got that, or speed, and so it's going to be a fraction of that speed will represent the difference between these two things. And if I knew what this was, if I knew the slip slip speed or slip frequency, if I knew that, I could find the rotor frequency here. And another thing that motor drive controls do is they estimate the slip frequency so that they can accurately find the rotor speed and even the rotor position if they want to accurately control the torque and the position of the motor. So you have introduced this little term that is this S slip. And then last time we showed you this expression. This is the key expression that you must know, okay, to do well on the exam, to understand induction motors. As the speed changes, the S changes, and essentially the loading of the motor changes. So to talk a little bit about relating this back to the electrical frequency, it's often helpful, and I very much encourage you to put this in your notes. Don't use these blindly. But you should have already, with our playing around with the synchronous machine, these numbers should kind of be etched in your head. At least this guy, right? A 4-pole machine was an 1800 RPM in revs per minute. You can get to that from, if you want to know what is the synchronous speed, right? You say, okay, the synchronous speed is 2 over poles times the 2 pi Fe. And then if you want to find that speed in RPM, it would be 2 poles, 2 pi Fe, and then we have this 30 over pi conversion factor here. That's how you get this. And this should say N sub S. So that's the synchronous speed. Typically, when we're talking about induction motor problems, the N is the rotor speed, just like it was when I first introduced that term for the synchronous machine. And then N sub S was the synchronous speed. You know, when we had the synchronous machine, or the synchronous motor, the N equaled NS, but it does not equal that anymore. And these are typical, oftentimes it's helpful to know, okay, I know if I've got a 4-pole machine at 60 hertz, I live in America, I'm going to have 1800 RPM. I live anywhere else in the world, I got 50 hertz machine, 1500. So, you know, I know these because I'm, you know, spent most of my life in the United States. But, you know, if I didn't, I'd probably be more familiar with these numbers here. And so, any questions about that?
Would the slip speed impact the efficiency of the induction motor?
No, not really, and you'll see that in a moment. The slip speed, it would impact it in a good way. Let me put it that way. If you think about efficiency as P out, see, efficiency is P out over P in. And, you know, when the P in it's P out over whatever you're putting out plus the losses. And so if you're at a very light load, which means a very small slip number, then the P out part is small. And there's a certain amount of P loss that's pretty fixed, like core loss, right? Core loss is a function of voltage. So at no, like at no load, you will have a speed won't be exactly the synchronous speed. It'll be a s. I was going to derive this, but I'm going to show you. It'd be 1 minus s times the synchronous speed. And this s is a very small number, but it is nevertheless not 0, okay? So this is often an exam question I ask. If you use s equals 0 in estimating no load speed, then that's a wrong answer. But if you're running at that no load condition, then the P out is proportional to it's really proportional to S. And so the P out's really small. So that means you've got a little small guy here, a little small guy here, and you've got core loss. So that's the efficiency is bad, but do you really care? You're not running at full load. If you ever want to go find efficiency and really have it be meaningful, you find efficiency at the maximum load you can operate. And so that would be the highest slip, steady state slip. And so that you would actually get the best efficiency, because it's like you have N slip rated plus the total losses. That would be, this might be something like 60% efficient, and this will end up giving you something like 90%. Does that make sense?
Yeah.
Okay. Yeah, so anyway, that's kind of the insight about the losses. It's important to know. Now, let's go to this. We introduced this circuit. Now, talking about losses, which DeAndre gave me a good segue into that. There's a second version of this circuit, which we derived last time, which breaks out the losses from this term right here on the rotor side. So if we think about what we are doing here, we're providing a power. This right here represents the P mechanical applied to the shaft, but it also includes the rotor the rotor I squared R loss. And what the two of these things together is the power that we are putting across the gap. It's the power that's going across that air gap. So it's often referred to as P, not P gag, but P gap, or P sub G. So what would that power be? It'd simply be I2 squared magnitude times R2 divided by the slip, and then 3 times, because you have 3 windings. So you break that out, because as I said, it's the mechanical plus the I squared R. You come up with this expression here. So this is the full, that's the actual, the equivalent to, say, when we talked about the DC motor, we had P mechanical equal to EA times IA. That's the equivalent to that for an induction motor. And so it's very interesting, because I could give you a problem where I just break things out in power and slip and ask you to find things, and don't give you the, don't make you solve the equivalent circuit. And that's a simple way to get an answer, but it throws a lot of people off, because you're you get into this mode where, okay, I just have to, here's my circuit, I have to learn how to solve it, I do this, and, but real problems are usually not that way. Sometimes you don't have all the information, so you have to estimate some things too in real life. So it helps to understand these things. Now, if you compare the expression that we had here for P gap with the expression for P mechanical, they're very close, right? So what do you see as the difference? What's the main difference between these two? Anybody? It's this. They're only different by that factor, 1 minus the slip. So you could find, if you knew just the slip and you knew just the air gap power, you could find the mechanical power. You just knew these. Now let me give you an example of why this is useful. What is the air gap power? It's, let's say that you're looking into the you got your motor right here, and you've got a meter, and you're measuring the input power to the motor. So the input power to the motor, remember this goes back way to the very beginning of the class, is the input power factor times the volt amperes. So if you knew the input power factor, you knew the volt amperes. So let's say P power factor is 0.83 lagging, and your V line to line is 480, and your I line is 10. Your S is square root of 3, 480 times 10. So that's that is 8.3 kilowatts. Okay, I mean kVA. That's 8.3 kVA. And then I'm going to multiply that times 0.83. 0.83 times 8.3. I promise I just made these numbers up. So that was a pure coincidence. So that's 6.9. It's approximately 7 kilowatts going into the motor. What if I told you that you had stator losses, stator plus core losses are 3% of P in? What if I said that? That would be the same as saying I've got an electrical frequency, I've got an efficiency. I'll just say it's efficiency on the stator side of 0.97, which is the same as saying let's see, that's telling me that P in is equal to the P that is delivered to the gap plus the P stator loss, including the core loss. So I'll call it S plus C, stator plus core. That's what Pn is. So the N efficiency I'm talking about here is Pg plus Ps plus C, and Pg is over on the top. So I'm trying to deliver the gap power. I'm talking about this circuit right here, saying that the power that's getting delivered to this part of the circuit here, that's P gap, versus the power that's going in to this part of the circuit. So if I know that, I've got the efficiency of that part of the circuit. And when I said this 3%, what I really meant was that I know Pn, and I'm trying to get this in a very clear way that you would understand this. I'm basically saying that Ps and C is equal to 0.03 times Pg. And that, another way to think about this would say, okay, my Pn is equal to P gap plus P stator plus core, and that is equal to Pg plus 0.03 times Pg, which is 1.03 times Pg. And this is what's on the bottom, right? Well, the easier way to do this, well, what I know is I've got N ES is equal to 1.03 Pg over Pg, or 1 over 1.03. I think it's 1 over 1.03 is 0.97. So that's 0.97. That's the efficiency. So knowing this, I know that P gap is equal to 0.97 times Pn. I could find that, right? And if I said, okay, if I knew the rotor losses, I could find P mechanical. P mechanical would be, if I gave you the rotor losses, it would be Pg minus the P from the rotor loss. Does that make sense?
Yeah.
Okay, so, go back, you can watch this video again too if you want to go through this, think it through. Now I want to go back up here for a moment. Because we had this relationship of slip, omega s minus r over omega s, or the slip frequency is this. Let's talk a little bit about what this means in terms of this here for just a moment. So this is a electrical wave for omega r, which is the speed of the rotor flux. And it would follow then that there's a frequency in, if let's say I had 3 phase windings in the rotor, what do you think the frequency would be in the rotor? This is that omega r. Well, if the frequency, I said the wrong thing here. This is omega r is the frequency of the rotor flux. But the difference between these is inducing a frequency, effectively an electrical frequency, into the rotor winding. So you actually have, just like the picture up here shows, you have voltages induced into the rotor, and they are 3-phase winding voltages, and they're operating at a different frequency than what you applied here. So you have an FE here, you're going to have an F rotor electrical here. And so what is that? Well, it is proportional to the slip frequency. It's a it's a small frequency. So if you're running at a light load, you could say S is small. So let's say it's 0.008. You would take 0.008 times the electrical frequency. If it's a 60 hertz, that'd be 377. That's 2 pi 60. Well, you just divided it by 2 pi anyway here. Let's say we had a 2-pole machine, 2 over 2. That's 2 over 2.008 times 2 pi 60 over 2 pi. So the frequency in the rotor ends up being 0.008 times 60 hertz. That is the same as saying 0.8%. It's less than 1% of the frequency of the electrical. So it's almost zero, but it's not quite. So if you weren't, you're always going to have to produce, you're going to have some frequency in there because those windings are shorted if you're applying a voltage. And that's related to the slip frequency. So this is another important equation right here that I could use, and I could find that. Another one is I don't have to have everything in terms of radians per second. If I gave you the synchronous frequency, which could have come from these tables that I showed you down here. It's like, or maybe they're up here. Where is that? Oh, where did I put them? There they are. Okay, I could have said, hey, you've got an 1800, you've got a 4-pole machine, 60 hertz. That's an 1800 RPM synchronous frequency. And it's got a rated speed of 1790. That's a very common induction motor speed. So I could say, okay, what's the slip? So let's say I have slip that's 1800, and this is the nameplate speed of the machine, the rated speed. At rated operation, you're going to have that speed 1790 divided by 1800. And so that's 1800 minus 1790 divided by 1800, and that is a slip of 0.0056. I don't know whether that's common or not. Maybe that's more of a no load. I don't know why 1790 sticks in my head. It's always the first thing I do. It's actually more of a no load. So let's just treat it that way. This is the slip at no load. This is the speed of the rotor. Speed of the rotor at no load. Now, no load, you can never turn a rotor and not have some mechanical load, right? You've got friction and windage, and you've got other things too. So there's never no load. There's no load as far as putting something onto the motor more than what the motor itself is loading itself down, because motors have bearings and things like that that cause a little bit of friction, and so there's a load on there. It's very small. It's impossible not to have one. But at rated, you could say, well, what's my slip under rated? Well, it's probably the speed is going to be slower, and let's try 1720. And I'm going to say, okay, this is the nameplate rated speed. You go to the motor, it's got a rusted little tag on it, and you scrape the rust off, and it says 1720. That's the rated speed. it's a 4-pole machine, 1800 minus 1720. So that's 1800 minus 1720 divided by 1800 is, that's a lot better. That's 0.044. That's your slip. And sometimes people will say these are in percent. So this would be 4.4%. And this is 0.56%. Does that make sense?
Yeah.
Okay, so let's go do we've done a lot of just kind of engineering things. Let's just do a plug and chug problem here. I got one more thing to introduce. Because we know the mechanical torque that's applied to the shaft, we can easily find the mechanical torque. The mechanical torque would be take that P mechanical and divide it by the mechanical speed, right? Just like we've done before. So I know all of this stuff. In fact, and just as an aside, what if I want to know what's the shaft? We said, what's T shaft? T shaft is going to be T mechanical minus the loss torque. That could be friction and windage loss or mechanical loss. So there's a bit of a difference, mechanical efficiency, or it could be the mechanical efficiency times T mechanical would be the T shaft. I could call this P shaft, just multiply both sides by speed, and I've got power, shaft power. I could get it to you in horsepower, for example. So, you've got that. If you're given a losses, which one of the homework problems give you a rotational loss right there, you'd subtract that off there. Or if you were given an efficiency, you'd multiply it and reduce it down. That's the shaft torque. But anyway, let's go back to, we know this. We know that P mechanical is 1 minus Fs times the gap power. So we could even plug this into this. And now we've got a new expression for the torque. Now I can actually come up with a much more elegant expression for torque. And that is remembering that my mechanical speed is 1 minus S times my synchronous speed. So I'm going to plug this into here. And I'm going to come up with a new torque expression, the gap power divided by the synchronous speed. And I can take this even a little bit further here. You remember that I know the relationship between synchronous speed and electrical frequency. It's 2 over poles times omega E. And so the mechanical torque can be given in terms of gap power divided by 2 times omega E. Now we're not going to, I can tell now, we're not going to have enough time for me to give you the third equivalent circuit, at least to be on the exam. But I'm probably going to write it down in the notes. But what you have right now, if you then say, okay, I know gap, this is one thing I'll tell you. I learned about induction motors in my undergrad in a class that was very poorly taught by somebody who was retiring. But I'll tell you one thing, I never forgot the expression for gap power. And it was 3 times the rotor currents, 3 times the rotor resistance times the rotor current magnitude squared divided by the slip. So I never ever forgot that. So this is easy equation to remember in terms of electrical parameters. Notice what I have here. If I plug this in, I have the slip speed here too. I could just give you the slip speed. I could give you the rotor I squared R loss. And you would be able to know the torque from the slip speed and the loss. Just multiply it times pole pairs. So there's a cool thing, but the big trick is you have to solve for this I2 if you have an equivalent circuit and you've got parameters. So there's one more equivalent circuit that's given in the book that we won't have time to talk about that enables you to find torque from the input voltage. And that's the equation that's used to derive what's called speed-torque curves, where you would have, just like we did for the induction motor, we have the speed, this could be the synchronous or it could be N. The shape is going to be the same. This is your torque, mechanical. And you get different types of machines have different curves for torque. And you get this is what's called the pull-out torque or max torque. Now there might be a homework assignment on this. So I'll put this in the notes, how to calculate those points, but you need to, there's an equation where you can get this right from the terminal input voltage, and a Thevenin equivalent circuit. And then this would be, say, your rated torque, somewhere right around here. And this would be your startup torque, like you're starting the motor, how much torque you need to get it started. And there's different types of machines they call them often different class machines. So you might have this, I hate that little, okay, there we go. There might be something more like, it might look more like that, or it might be a different curve like that. So they often classify machines as the way the speed torque curves look. Okay, so let's look at an induction motor problem, and I'm actually going to do this differently, different numbers. I'm going to put in different numbers here, and I'm going to say, let's look at a situation where we have rated slip. I'm going to give you the slip is 0.03. I'm going to give it to you in 2%. 3.2% rated slip. So that's the same as saying S equals 0.032. And I want to ask you what is, I'm going to give you the parameters R1, X1, X2, XM. We're going to say that RC is almost infinite, so we'll ignore that, and R2. And I've got what I'm going to give you is R1 is 0.17 ohms, X1 is 1.05, X2 0.87, R2. Just bear with me, I want to go through this another 5 minutes. R2 is 0.24 ohms. This was 0.87. And then XM, which is 82 ohms. This little example problem here, this is too, I think that's a mistake too. It's too close to the other values. But anyways, these are the parameters I'm going to give you. And if I want to find the rated torque, the easiest way for me to solve this problem is to use the first equivalent circuit that I gave you, which is this one. We don't have the RC in there. This is the rotor current I2. I've got a V1 applied right here. So how do I go about solving this problem? Well, I have to use phasor math, obviously. I'll have to give you the rated voltage I'm going to give you. It's always given to you in line to line. So it's 400, I was just double checking my numbers. It's 460 volts RMS, line to line. And it's 60 hertz is the frequency. So if I want to go about solving this problem, I have to find V1. So what is V1? Well, this is kind of my reference point. It's a line to neutral circuit. Remember, you have to convert to line to neutral. Divide by square root of 3. I'm at a 0 angle. And so I get that is 265 0 degrees volts. That's V1. Now, what I have to do to find the torque is I have to find this current. So I'm going to have to first find this current, and then I'm going to have to do a current division. So what I'll do is I'll say, let's take, there's this impedance right here. It's in parallel with this guy here. So I could call this the Z2, the rotor impedance. If I look in here, I could call this, it's basically Z2 in parallel with JXM. And then I've got to add the stator impedance to it. So basically, I've got to find a Z in, which is Z1 plus JXM Z2 over Z2 plus JXM. So I got to find that impedance there. And then I1 would be equal to V1 divided by Z in. Now that I have that, I need to find I2. I have to do a current divider. So I2 would be I1 times JXM over Z2 plus JXM. I've got that. Then I can find the rated torque. It'll be helpful for me to find, I could just say that P gap is equal to 3 times R2, magnitude of I2, divided by S. And I might as well I could find the losses in the rotor, which is 3 times. Well, oh no, see, I'm messing. I could do it even better. Once I know that, I know P mechanical is 1, since I know slip. If I didn't know slip, I'd do it differently, but I know slip. That's 1 minus S times PG. And then the T mechanical rated would be the P mechanical divided by the mechanical speed. So that's simple, okay? Those are the steps, the minimum steps to get there. So, you know, I actually pre-calculated these, but I found Z in, and that was equal to 7. Oh, let me do one step here first. The first thing you do is you need to find R2 over S. This is the biggest mistake that's made in exams. They forget this. So I know S is 0.032 and I know R2. So it's 0.24 divided by 0.032 because this is going to change with load. So if I take 0.24 divided by 0.032, that's 7.5 ohms. That's essentially the load resistance. This is what I called my rated slip. And so the Z in under rated conditions ends up being 7.9 ohms, and then the angle of that impedance is 19 degrees. Now I could find to find the output torque, I only care about the magnitude, but I could also find the input power factor if I want. So the whole phasor current, I1, is V1 divided by Z in. So that's 265 divided by 7.9, 0 degrees, 19 degrees here. So that's 265 divided by 7.9, which is 33.5 amps. Negative 19 degrees. I know my power factor. So there's my line current. My power factor is cosine of 19 degrees. Which is 0.95. Looking into this motor, I could find my rated volt amperes. That's going to be square root of 3, 460, 33.5. Now, I mean, I'm going to just finish this. I know I went over, but I think it might be helpful for you all to see this. That's 27 kVA. So let's go back. Let's go find the. You guys want me to keep going, or do you want me to stop? Because we're 5 minutes over.
You can finish.
Okay. Well, let's find we did this. We did this. So we're going to find the rotor current. And I don't really care, well, I don't think I care about the angle of it, but we'll put the whole thing in there. I1 times this, I've got to do this current division here. I didn't pre-calculate this. GXM. I did this really fast, so we'll see if everything works out. Makes sense here. So that's 33.5 negative 19 degrees times the XM, which was 82, J, that's a 90, right? Now I have to divide by Z2 JXM. Now I pre-calculated Z2, and my Z2 was 7 point, it was this, 7.5 plus J 0.87 plus J 82. This is the Z2. Well, I know what that is. That's R. That's, I found that R2 over S here, right? 0.87 is the leakage inductance of the rotor. So I just convert this to a magnitude now. So I'm squaring the 7.5 and squaring the sum 87.82, and that's 88. So this ends up being 33.5 times 82 over 88. I don't really care about all the angles because I'm just after the amplitude. So it's 33.5 times 82 over 88. Now that makes a lot of sense. The rotor current's going to be some reduction because there's magnetizing current that went down the branch here, right? So a little bit of it goes there and the rest goes over there. But it's not negligible what goes down the magnetizing branch. So 33.5 times 82 over 88 is 31.2 amps. So I could find the P gap 3 times 31.2 squared times the rotor resist times R over S, which was 7.5. So 31.2 squared times 7.5 times 3 is 21.9 kilowatts. That's the gap power. Now notice that I've got here, remember I found the volt amp. Let's check this. So that's my input volt amperes, 27, and my gap power is 22. I know the input power factor, so I could find the input power from the stator side. That would be 0.95 times 27 kVA, which is 25.7 kilowatts. So I'm dissipating about 5 kilowatts in the stator. It's about the difference between PG and PN. You know, I could know exactly what my stator losses are now from this if I wanted. You know, it's essentially P stator I squared R, which is 3 times RS magnitude of I1 squared, but I don't even have to do that because it's going to be PN minus PG. Now the rotor I squared R loss little r here is going to be 3 times 31.2 squared times the rotor resistance, which was 0.24. Oh, yeah, remember I said I don't even have to do this. This is too much work. I just wasted time. Okay, and I want to get my exam done. So I know the slip, right? So P mechanical, I could have found this and subtracted it from the P gap, but I could just say T mechanical is equal to 1 minus the slip times PG. 1 minus 0.024 times 21.9 kilowatt, and that is, so 21.4 kilowatt. The way this thing's working out, I don't have, yeah, it's a little bit weird, but I mean, I'm showing you the process. I think the losses seem a bit low compared to what I had in the stator. I have to go back and look at that. I'll probably clean these notes up and make sure we've got everything. I didn't miss a decimal point or something. But this is close. That's the mechanical power. So essentially the efficiency from input to output, we can check that. It's going to be 21.4 kilowatts divided by my input power, which was 25.7. So 21.4 divided by 25.7, it's 83%. That seems a little bit low. So I'm going to redo it, but I'm going to stay tuned. But the next thing I want to do is I'm going to check this. I'll clean this up. T mechanical is the mechanical power divided by the mechanical speed. So all I need to know is the mechanical speed. Well, what is the speed of the rotor? N. It's going to be 1 minus the slip times the synchronous speed. Now, one thing I didn't tell you, which I should have, was I had to tell you how many poles there were. So let's say it's a 4-pole machine. So, because I have to know that, and that means I know that this is 1800, 1 minus 0.0. You know what I think I did? I was changing my slip number. I know what I screwed up. It's not 0.024. It's 0.032. You see, I put 0.024 because it was going so fast. This is wrong. 0.032. 1 minus 0.032 times 21.9. That's a lot better. $21.2. My P gap was, it's still a little bit weird. Only 0.7 kilowatts. It's like the stator losses were so high. So I got to go back and double check something. But anyway, 21. So it's not going to change this number. This seems a little low, and I think that I might have made a mistake somewhere.
Yeah, your mistake is the fact that when you converted the slip speed, you put 32% is not 0.032, it's 0.32. Because what you have is technically 3.2%.
32% is, it's 3.2%. It's not 32%. It's 3.2. It's not 32. I may have said that, but it's 3.2. 0.032 is the right number.
Oh,
a 32% slip would be a horribly designed motor. Your slip should be less than 1%. slit, you know. So anyway, bottom line, there might be some small error. I'm going to go find it. But 0.032 times 1800 gives me my speed. 1 minus 0.032 times 1800. That's 1742. I think one of the big issues is that the slip that I assumed is a little bit, it should be higher than 0.032. That was just kind of an arbitrary number. I think that's the issue. I don't think I did anything wrong. It was just the number that I picked for slip is a little bit low. Okay, so this is the RPM. Now I can convert this to mechanical speed. It's going to be 1742 times pi over 30. So 1742 times pi over 30, which is 182.4 radian per second. And so my rated torque is my mechanical power, 21.2 divided by 182.4. And there it is right there. So that's 21.2, 182.4, 116 Newton meters. There it is. Now the one other thing, I could put my P mechanical in horsepower. That's probably the way things are looked at from the motor standpoint, because we have to remember that horses used to do everything. Okay, so we got P mechanical, 21.2 kilowatt. I'm going to divide it by 746, just to give me an idea of the horsepower rating of the motor. So if I had to buy it in the 1970s, definitely it would give me this. Now, the rusty nameplate would have that. Possibly today they use kilowatts more often, especially if you're buying things anywhere outside of the United States. So that's a 28 horsepower motor. Okay, there you go. I went way over time. Thank you to the dedicated, let's see how many people stayed. 15 people. Okay, if there's any, that's the end of the class. If I can stay around if there's any questions. But